Welcome to this explainer. Today, we're breaking down matrices into a high-yield study guide designed specifically to get you completely ready for your board exams. We're not just skimming the surface here. We're going to dive deep into the exact step-by-step mechanics and the proofs that examiners absolutely love to test. If you've been feeling even a little overwhelmed by giant arrays of numbers and brackets, don't sweat it. We're going to make this incredibly structured, highly visual, and focused strictly on scoring you maximum points. Let's get right into it.
Here is our roadmap for this explainer. We're covering a quick introduction to matrices, their order and types, basic matrix operations, the multiplication rules, and then wrapping it all up with transpose and symmetry.
Starting off with Section 1, Introduction to Matrices.
So what is a matrix, really? Think of it simply as an incredibly organized grid that tames complex math. The numbers or functions sitting inside that grid are called its elements, or entries. When you're staring down a brutal system of equations on exam day, a matrix allows you to strip away all those messy x, y, and z variables and just look at the raw coefficients. Honestly, whenever you have data that needs structural sorting, whether you're tracking factory inventory or the vertices of a geometric shape, a matrix is going to be your best friend.
Moving right along to Section 2, Order and Types.
Okay, this is absolutely crucial for your boards, the order of a matrix. The order tells you exactly how big the matrix is, and you must always read the horizontal rows first, which we call M, and then the vertical columns, which we call N. A great trick is to always remember RC, like RC Cola, rows first, column second. Listen, if you misidentify the order as N by M on exam day, every single subsequent calculation in a heavy 5-mark question is going to be wrong. So lock that in, rows first, column second.
Now here's a rapid-fire list of matrix types you need to have memorized. A column matrix has just one column, a row matrix has just one row, a square matrix is perfectly balanced, its rows equal its columns. A scalar matrix is a square matrix where all the diagonal elements are exactly the same number and the rest are zero. But pay very close attention to the identity matrix, denoted as I. This is basically the MVP of matrix algebra. Its diagonal elements are exactly 1 and everything else is 0. Whenever you multiply a matrix by its matching identity matrix, you just get the original matrix right back. It's exactly like multiplying by the number 1 in standard math. Examiners will constantly hide I in proofs to see if you actually caught this property.
All right, Section 3, Basic Matrix Operations.
When it comes to addition, the golden rule is that the matrices must have the exact same order. No exceptions. If matrix A is a 2 by 3, matrix B absolutely must be a 2 by 3. If they aren't the same, the operation is simply not defined. But if they do match, you just add the elements sitting in the exact same positions together. Subtraction works the exact same way, but seriously, if those orders don't match perfectly, just confidently write undefined and take the easy points.
Now, what if you're scaling things up? Say you're multiplying a matrix by a single constant number, a scalar, like if you were doubling a factory's entire production output. The trick here is that you must distribute that number. You multiply that scalar value by every single entry inside the brackets. Don't leave a single element behind or your final matrix is going to be completely off.
Up next is Section 4, the Multiplication Rules. We are officially entering the boss level for board exams.
So the heart of this boss level is the row-by-column method. Let's break this down slowly, because this is literally where the biggest points are won or lost. You don't just multiply corresponding elements. Instead, you take the first element of row 1 in your first matrix and multiply it by the first element of column 1 in your second matrix. Then you add that to the second element of row 1 multiplied by the second element of column 1. You're basically sliding one finger across the row of matrix A while moving your other finger down the column of matrix B. This dot product creates just one single entry in your new matrix. You then repeat this whole dance across every row and column. It takes a ton of practice, so definitely drill this heavily before test day.
And watch out, because here is a massive exam trap. In standard math, we all know 2 times 3 is 6, and 3 times 2 is 6. Simple, right? But in linear algebra, matrix multiplication is generally not commutative. That means matrix A times matrix B does not necessarily equal matrix B times matrix A. In fact, sometimes AB works out perfectly, but BA isn't even mathematically possible because the row and column orders don't line up anymore. So golden rule, always assume AB does not equal BA unless a specific problem proves otherwise. Finally, Section 5, Transpose and Symmetry. These concepts are massive point scores.
Finding the transpose of a matrix is actually super easy visually. You literally just take your horizontal rows and flip them into vertical columns. Your first row becomes your brand new first column, your second row becomes your new second column.
It's usually marked by a little apostrophe or a capital T next to the matrix name. Oh, and remember how this flips the order? If your original matrix was a 2 by 3, your transposed matrix automatically transforms into a 3 by 2.
You're going to want to take a mental screenshot of these properties right now because they absolutely will show up in your proofs. If you transpose a matrix twice, you just revert back to the original matrix. But the real star here is the reversal law at the bottom. The transpose of A times B equals B transpose times A transpose. Examiners love testing this because students intuitively want to just write A transpose times B transpose. Do not fall for it. The order must flip to account for those complex row by column multiplication rules we just covered.
That brings us to our final core concept, symmetry. This all boils down to what happens when you transpose a matrix. If you transpose a square matrix and get the exact same thing back, it's symmetric. But if you transpose it and end up with the exact negative of your original matrix, then it's a skew-symmetric matrix.
Here is an expert tip to check your work on the exam, and frankly, this frequently pops up as a quick one-mark proof. In a skew-symmetric matrix, every single diagonal element is always 0. Why? Because the mathematical rule states that element aij must equal negative aji. For the main diagonal, the row equals the column, meaning aii equals negative aii. The only number in the entire universe that equals its own negative is 0. So if you're calculating a skew-symmetric matrix and there's a 5 or a negative 2 sitting anywhere on that main diagonal line, you instantly know you've made a mistake.
To wrap up our explainer, I'm going to leave you with the provocative question that is actually a major theorem in linear algebra. Can any square matrix be broken down and expressed as the sum of a symmetric and a skew-symmetric matrix? The answer is a resounding yes. You do it using the formula 1/2 A plus A transpose plus 1/2 A minus A transpose. I highly recommend you crack open your notes and master proving that exact formula tonight. It beautifully ties every single thing we just discussed together. Good luck with your studying. You've totally got this.